But not yet started. Shall we start, Cynthia? Shall we
Yes,
start?
ma'am. Yeah, sure. Yeah, I'm ready. Yeah.
Okay, good morning to one and all present here. Once again, I welcome you all for today's session. Am I audible?
Yes, ma'am, you are.
So, on behalf of the AAA Department, PHG College of Technology, it is my pleasure to welcome our resource person, Ms. Sandhya Sridhar, today to handle the first session of the day. And she's our proud alumnus of PSG College of Technology. She received her bachelor's degree in Instrumentation and Control Engineering from PSG College of Technology in 2014. She worked as an engineer in Mercedes-Benz Research and Development India from 2014 to 16. After that, she pursued her master's degree. She moved to the United States of America and graduated with a master's in electrical and computer engineering from Georgia Institute of Technology in 2018. She is currently working as a research engineer at the Ford Motor Company, California, and has the experience of interning in various research and industrial organizations. Her interests include computer vision, machine learning, deep learning, and autonomous driving. Welcome Sandhya. Sandhya.
Yeah, thanks a lot for the introduction.
I hand over the session to you.
All right. All right, let's get started. So, before jumping into the topic, I wanted to introduce myself again. I'm Sandhya Sridhar, and I'm from Coimbatore. I got my bachelor's in instrumentation and control engineering from PSG Tech, and I was then working for Mercedes-Benz. And I had the chance to go to Germany for on-site visits back then. And later I moved to the United States of America, to Atlanta, to get my master's in electrical and computer engineering from Georgia Tech. And currently I'm working in California as a research engineer at Ford Motor Company. This is my career progress so far. I started out as a research engineer. I'm back as a research engineer now with a bunch of internships in between. The one thing that I would like to focus on, though, is the EcoCard challenge that I was part of. This was during my grad school. This was also part of my master's thesis. So EcoCard 3 is it's a college level competition for United States and North America and Canada mostly. There were 16 different teams, and our goal was it was sponsored by General Motors, and the goal was to convert a gasoline Chevy Camaro into a hybrid electric vehicle. And my role here was mostly to do with ADAS, so adding all kinds of driver assistance systems to the vehicle and making sure it all runs real time in the vehicle. So this is mostly where I'm deriving most of the material for the stock from. And if there are any this technology is definitely a little outdated since it's coming from 2016 to 17, but I would say these are still a good building block for what we are working on right now. And outside of work, I always think people introduce themselves mostly with their profession. They identify themselves by their profession, and I wouldn't always call myself a research engineer. Outside of research, I also enjoy hiking a bit, and recently took up to baking. I'm a student of violin, and I also sing. And yeah, the lockdown forced me to do some gardening and some painting, and these are from some of my paintings from this year. So this is me outside of work, and yeah, feel free to hit me up if you want to talk about any of these offline. So jumping into the agenda. So we'll first be talking a little bit of motivation of why we need ADAS or what autonomous systems are in production right now. And then speaking a little bit about the differences between autonomous vehicles and connected vehicles, and then the sensors used in these systems, and some of the ADAS technologies that we have, that we already have in production, and some of us would have used today, and some which are future-proofed and in a concept phase today. And then we'll jump into specifics of computer vision in ADAS, what role computer vision plays there, and finally, like a detailed analysis of various object detection methods and vehicle or object tracking methods that I worked on as a grad student and also for the EcoCar competition. Most of these slides are not to do with Ford Motor Company, not to do with my employer. They're obtained from various sources. So I've tried to mention the source, and if there's something that's not, pardon me for that. But yeah, these are all like nothing to do with Ford Motor Company. So getting started, why do we need ADAS? There's a survey which says over 90% of the collisions today are due to human error, like human-induced error. And it also goes on to say 90% of all the rear-end collisions that happen could actually be prevented with just 1.5 seconds of warning to the user. And 2 seconds of warning would completely eliminate all these rear-end collisions. This is a huge number here, given like most of these rear-end collisions happen at like high-speed driving, and it happens in like freeways and things like that. And this is definitely like just like 2 seconds of warning is all it takes, and that is definitely achievable with ADAS systems. And further, the other thing is the number of cars on the road today. It's increasing dramatically, and we already have like 1 billion cars on the road. And this number is increasing by the day. And the other thing that's increasing as well, interestingly, is the average age of these vehicles. So just in Europe, it started like all the way from 8 somewhere to like 10 years now. So a car that's put into production, that's sold to a customer, a fleet of vehicles, it stays on the road for 10 years. So the technology that we put into these should also be future-proof or should be upgradable. So a customer who buys it today would still find the vehicle relevant 10 years later. This is a concept of using ADAS systems in an urban setting. I especially like this image more because this only uses cameras here, at least for this, for the purpose of this image, which is very much relevant to our talk since we're going to be talking about computer vision. So, and this is especially interesting because this is for a large vehicle. What we usually see is computer vision in cars and or like smaller vehicles, but they, I think this slide is from Mobileye, and they say that even for a vehicle as big as a bus, just by using like multiple cameras and the right technology for using these cameras, we can actually go ahead and detect pedestrians, and in an urban scene, we could still do with this. So that's like the power of computer vision in ADAS and in an urban driving scenario. So looking into the differences between a fully autonomous vehicle and a connected vehicle, and I believe like both autonomous vehicles and connected vehicles would be an integral part of the future. We'll be having like both these, but the differences between these are, for an autonomous vehicle, the AI, the technology resides inside the vehicle. So whatever we see today would mostly be relevant to self-driving vehicle and not to connected vehicles. The reason being, for connected vehicles, it's mostly the infrastructure that does all these things. So there would be like city infrastructures or like cloud-based processing, and most of the AI processing would happen there, and the vehicles that pass through that corridor would just receive the final inferences out of these networks. Whereas in a self-driving vehicle, we only have like sensors on the vehicle. So it's going to like blast out, take all the data it can from using these sensors, capture all that. It has like an ECU of itself, multiple in fact, and it will be processing data from these sensors on the vehicle locally, and it will take decisions locally. And since these decisions are taken by the vehicle, it's, at least until now, it's not shared with other entities, and there are like privacy issues. But when it comes to connected vehicles, these would be like shared across all vehicles. And in fact, there'd be like a lot of vehicle-to-vehicle communication, vehicle-to-infrastructure communication, and that would enable a more socialistic setup there. to see some examples of what autonomous vehicle concepts look like. Again, nothing to do with Ford Motor Company, but this is just like two images of what it looks from the outside with all the sensors loaded on top of the vehicle, and two from inside the vehicle. And the infotainment and the whole setup of how we would imagine a vehicle in the future would look different, because now the seats are going to be turned the other way around. There's going to be no steering wheel in a fully autonomous vehicle setup. And it's almost going to look like a very cozy cabin in there. And coming to connected vehicles, here it's mostly everything's happening outside the vehicle. There's going to be like infrastructure, cloud-based inferencing happening everywhere. And what the vehicles finally receive from these is just going to be like data of what's happening out there. And the decisions are going to be based out of everything that's coming from the infrastructure, or say another vehicle here. So in this setup, it's easy though, because say the vehicle behind does not have like the right sensors, but it just has the technology to absorb data from other vehicles. In that case, the vehicle going in front can do all the inferencing, pass it on either to the infrastructure or directly to the vehicle behind. And that would be like a good sharing of information going on there with connected vehicles. But the technology involved there more is towards communication and not like AI, or rather AI is happening on the cloud and not internally in the vehicle. So what's been happening in this domain? A lot has been happening in the autonomous driving sector so far. And a lot has been happening very quickly as well. Just between 2016 to 2020 now, there's been like a lot of money that has been transacted, too many acquisitions and mergers, a lot of startup companies, in a lot of relevant fields actually, because we see ADAS as one entity, but to make this become a reality, we'll have like software companies doing their part with the algorithms. We'll have hardware companies trying to like make the right ECUs to process these algorithms, and also all the sensors that go on, the right sensors and sensor on chip, and even the data. The data is like a huge thing out there right now, like just collecting the right amount of data for ADAS and annotating them. So that's like a whole lot of money involved and a lot happening out there as well in this field right now. To drive the point further, so to drive this further, these are images that I collected from one of the conferences here, the Computer Vision and Pattern Recognition Conference last year. And it almost looked like the autonomous driving sector had had the conference, and almost every company that I could think of had their presence there, and they were talking about their autonomous vehicle technology. So it's definitely happening, and it's like a big thing out there. It's pretty much still in research, and there are like some proof of concept for fully autonomous vehicles, but definitely there's like a lot of improvement and a lot of technological advancements happening there. And definitely, yeah, this is not going to happen in one step. It's not going to be like, hey, today it's going to be completely manual and from tomorrow they're going to be autonomous vehicles. No, it's going to happen in stages. And I believe we are currently still in the safe driving driver assistance, the safe driving assistance systems part, where the human driver is still involved. There are not many cases where the driver is allowed to take his hands off or eyes off, but that's the next step in the future, like semi-autonomous driving systems, where driver can, at least for an intermittent period of time, take his hands and eyes off the vehicle and do something else. And of course, all the way to like fully autonomous systems, it's probably like, 2030 or even a little bit later than that, based on how quickly we're able to like put all these technologies into production. But yeah, it's definitely happening, and it's a very popularly researched topic. And SAE has categorized, or like it has divided these into like levels now, going all the way from level zero being completely manual, which is what we used to have, and all the way to level 5, which is a completely autonomous system. And everything in between is like one step towards a completely autonomous system. And currently, anything that we have on the road right now is somewhere in level 1 and level 2. And level 3 is definitely a topic of debate because it involves like the takeover request mostly. It's still debated on if how the system would like intimate the driver, and if it's going to be like too nicey, if it's going to like distract the driver by just requesting him to take over. So that's a topic of debate. But for this talk, at least, anything that we will be covering will go from like level 1 to level 3, and we're not going to talk so much about level 4 and 5. Those, at least currently, they're going to be definitely an extension of what we see here. The technology would be the same, but a lot of connected vehicle concept and the way this whole thing would be executed, the infrastructure would change there. So just jumping into advanced driver assistance systems, this is one of the popular images that resurfaces every time somebody speaks about an ADAS system. It shows like the different sensors that are used and all the applications that can be like applied using or can be put into use using these sensors. So this currently shows like two kinds of radars, long range and short range, LiDAR, and also a camera. And of course, there are going to be other things as well. We'll see a little bit later, because we'll definitely need ultrasonics and a few other components that go into making these ADAS systems. But before that, why do we even need ADAS? This is all cool. It's good that we'll have like completely autonomous vehicles, but why do we even need these stages in between? How is it going to benefit the driver or anybody in that case? So for the first thing, yeah, it brings down emission a lot, because using these systems now we can like do a lot of route optimization, traffic flow management, and that's going to bring down emissions by a huge amount. So the target is definitely zero emission, and I believe we are slowly getting there with both electric vehicles and using these systems with electric vehicles. And the other thing is like supporting drivers who are not confident, new drivers basically. And this is a very personal thing to me as well. When I started driving, I did notice that a new driver who's on the road should be as good as the other driver, if not better, because everybody's sharing the road. Then there's no excuse that one can give saying, hey, I'm still new, I'm going to drive badly on the freeway, and you're going to put up with that. No. So in that case, if there's a system that could like help the driver. So for me, it was mostly the blind spot detection, things like that. If there's like a warning system that's also looking out for these things along with the driver, that helps driving a lot. It makes driving a lot easier. And the same thing applies for elderly people as well, and sometimes people with disabilities as well. So it would definitely help people drive better. And vision, it increases like the vision of a human driver, like say low light conditions, night driving, or foggy conditions. It would definitely like help notify the driver of warnings if human vision fails at that point. And yeah, there are like other benefits as well, increasing the helping traffic density, an economical standpoint, and sensors being really good as well. A few other things are it increases driver productivity. So when these systems are put into use, at least right now, it still requires the driver to stay engaged. But going forward, if in a traffic zone in a congested area, most of the time that we spend is just holding onto the steering, braking the whole time, and looking out for the vehicles to move inch by inch. And in these cases, if ADAS were to take over, it would definitely help the driver, at least in congested areas. We can like let go of the steering, do something else, probably like listen to a podcast, read a book, anything based on like what's allowed at that point. And that's going to increase drivers' productivity during the drive. And also like parking, there are, especially in like again congested cities, I think some of these concepts are already in production right now. Valet parking, for example, where the user just stands outside, asks the car to go park itself, and especially in cases of parallel parking or parking in very congested spots, it's easier to just let the car do it and not deal with the fuss. And doing all this, yeah, definitely helps bring down the insurance as well. So that's also going to be a major cost saver as far as the driver is concerned. So what are the key sensors that we use in ADAS? We saw a few of these in the slide earlier, but mostly, yeah, it's the same. It's radar, LiDAR, video cameras, and a few other things that we already have are GPS, mapping, and all the ultrasonic sensors, which are already in cars right now. For that matter, even radars are mostly in cars already. Communication is something we have only to an extent right now, just like get like downloads and updates. It's currently not active in the sense where there's an infrastructure giving us details, but yeah, it's under discussion and with a lot of like privacy concerns and everything. But once that gets sorted out, this would be a cool technology to have as well. This talk, though, since it's going to be focused on computer vision, we'll be focusing mostly on applications coming out from the video camera. And let's see where these cameras go on the vehicle itself, or well, where do these sensors go on the vehicle? So the cameras are mostly always placed on the dash here, either here or sometimes even in the front, based on like what we're trying to detect. And LiDARs go on top. LiDAR stands for light detection and ranging. And radars, they usually like five in the front, five again in the back, and mostly to like check the distance between the ego vehicle and the vehicle in front. So that, so yeah, the front or back for that matter. So that's like for all the collision warnings, we have the radars here. Cameras, of course, we use them to like detect objects, see, infer anything we can from the images that we get out of the cameras. And LiDARs currently, again, like a point of debate whether we need LiDARs or not. Big corporations like Tesla are arguing against having a LiDAR. And there are some corporations which have actually used something called a pseudo LiDAR, where they create the LiDAR without the actual sensor. They just simulate a LiDAR there. So, but yeah, LiDAR is mostly used to like obtain a 3D point cloud of the scene ahead of the car. And this is something that stays on top. It's a revolving sensor. It's a 360-degree sensor, so it keeps rotating the whole time. And yeah, GPS is something we have on the vehicle. And then there's this ECU. I feel the role of ECU is always underplayed, but it's a huge thing for the vehicle, because all these sensors are collecting like huge amounts of data and like giving it to the vehicle, and the central computer or the ECU is the one that processes it all. So the technology there's also improving, and that's one of the main driving factors for all the features that we have in ADAS right now. And ultrasonics are something that we already have in vehicles. It's mostly mounted on like wheelbases to like check the proximity to the vehicles around us. So what are some of the technologies that we have pertaining to ADAS? Like there are some that we have today that are already in use, and some which are like concepts for the future and something that we can totally look forward to. And these are all like concepts that are going to be part of the vehicle in a very short span of time in the near future. So anti-lock braking systems, it's mostly to, it allows the wheels to maintain traction control, avoid skidding, prevents the brake from locking up. Adaptive cruise control helps to like maintain a safe distance from the car ahead, a set distance if you can. And it uses like radars for that. And blind spot detection, this is something we have in most cars as well. It just looks to, instead of the driver turning around to checking blind spot every time, the blind spot detection algorithm works for us there, and it keeps checking to see if there's any vehicle in the blind spot of the ego vehicle. Driver drowsiness detection, it's not like completely prevalent in vehicles yet, but definitely spoken of, it'll need a front-facing camera, something that'll be facing the driver to look for all the behavioral changes, something like, hey, how many times has the driver blinked? Is the driver distracted? Or something, if not for a camera, these are applications from camera, but if not for a camera, it could also like detect how often the driver is like moving the steering. Is it really necessary, just to detect if the driver is drowsy or completely awake? And hill descent control, mostly for rough terrain, making sure there's some extra aid while the car is like speeding downwards. Electronic stability control, again for controlling skidding and reducing loss of like traction in the vehicle. Few more technologies here. Intelligent speed assistance. What this does is it recognizes the signs on the board, on the road, the speed signs, and alters the vehicle speed accordingly. Either alters or at least throws a warning to the user saying, hey, you are going above speed or you're way below speed limit. So that's intelligent speed assistance. Lane departure warning, also found in a lot of vehicles today. This is interesting because this also detects, this uses cameras to detect the lane lines, and it also localizes. We'll look into this a little bit later, but it localizes the vehicle. So when I mean localization, it's just not about detecting where the lanes are on the road, but it's detecting where the vehicle is with respect to the lanes. So this way we know if we are like going too close to one lane, hogging the other lane, or if we are trying to like make a lane change, it would help us do that at that point. That's lane departure warning. Emergency braking, just making sure you're doing things right, or if not, it brakes for us. It checks the relative speed and gap required and applies brake whenever necessary to like avoid collision. Pedestrian detection, yes, the name says it's just recognizing, detecting people there. And if the car is about to like hit a pedestrian or something, it brakes automatically, or at least throws like a huge warning message. It almost, yeah, it scares the driver at some point. It does that. Rear cross traffic alert is something we have in a lot of vehicles today. This is mostly in cases where we are backing out of a parking lot, and it looks for vehicles that are going past us just so we don't like collide with them. So these use the sometimes cameras, sometimes just the radar sensors that are placed in the back to look for vehicles. Traffic sign detection, very similar to intelligent speed assistance, but this can be a little more generic, because if there's a stop sign, say, and the driver doesn't really pay attention, it's going to like help the driver pay attention, or at least make sure he doesn't do that again. So these are some of the technologies today, and let's look into how computer vision actually enables us to like take this forward. So computer vision by itself deals with processing anything that comes from the camera, and it has its roots in a lot of other fields here. And specifically in the ADAS relevance, in the context of ADAS, it can help us in a variety of ways. A few that we already saw, but to specify a few more, mostly like parking assistance, helping in low visibility area, or like reverse features, things like that. So computer vision is an integral part of ADAS, and I wouldn't imagine any ADAS system that could actually function without a computer or without a camera in it. This gives us a quick view of what it looks for the user. So it's good to have ADAS systems, but just to know, instead of like just giving us like a map which says, hey, 250 meters, turn right or turn left, it actually points us to the road and says, okay, this is exactly where you'll have to do this. And one good thing that can like, this is currently not in a lot of vehicles, but would definitely be good to have. This is like actually detecting the building or the exact location that we want to go to. Usually we just drive by and it says, yeah, you've arrived. And most of the times you're like, oh, where have I really arrived? So this would help the user actually see, oh, this is the exact spot where I have to be, and actually locate where he or she has to be going. And yeah, similar applications here. It shows the distance between the eco vehicle and the vehicle in front, just so we maintain the same distance. I think this is when adaptive cruise control is turned on. And this is lane departure warning, or like lane change warning, just to say, okay, if you are planning to, whenever maybe you turn your indicator on to tell the system that you're going to like make a lane change, you can do this and say, okay, this is the path that you follow, and there's a vehicle right in front there. So these are all like just, this is an idea of how the HMI looks with ADAS systems in place. From the architecture point of view, what goes into an ADAS, there are definitely sensors and actuators there. And these sensors, yeah, we've seen a good, we now have like a good idea of what sensors are in place there. From the software side, it's going to be like perception, planning, and control. These are the main building blocks there. And today's talk will mostly be about perception. And yeah, perception involves both environmental perception and localization, where environmental perception is just detecting objects or segmenting them, understanding the scene ahead of us, whereas localization is specific to the current vehicle, okay, specific to my location, where are all these things at. And sometimes it can go all the way up to like millimeter level accuracy there, especially when we're doing like lane changes and all that. So perception is what we'll be looking mostly at, and perception then feeds into planning, route planning or path planning, and finally into control. And control then gives commands to all these actuators. In the simplest form, it could be just controlling the steering and the brake. It sees an image and it applies controls, it applies the steering or brake accordingly. But in complex systems, it could go all the way up to OS, who's going to turn on the indicator, especially in a fully autonomous system, it could go all the way up to that. So what are the building blocks here for computer vision in ADAS, like for the perception stream that we're going to look at? These are the most important ones that currently are in ADAS systems: object classification, detection, segmentation, depth estimation, and tracking. Object classification is just looking at an image and telling what that image is. So yeah, it looks at this and says, yeah, it's a cat. Object classification with localization is where it bounds the objects and says, okay, this image has a cat and this is exactly where the cat is at. The difference between classification plus localization and actual object detection is, in classification algorithms, it's trained only to classify the biggest object in the picture. So and more often than not, there's also going to be just one image or one object that we want to classify. Whereas in an object detection algorithm, now it has to like run all the way across this image, spot even like the smaller ones here. This is more useful because in a practical driving scenario, they're going to be like pedestrians, they're going to be like dogs with pedestrians, pets with them, or maybe even kids, or road obstacles, cones might be placed. So everything has to be detected in the image. It can't be just one pedestrian that we detect there. So object detection helps a lot in that case, and we'll be looking into a detailed view of what's going on with object detection. In segmentation, what they do is every pixel in the image is assigned a class. So say we are trying to segment out all the free space here or the drivable space, that has a different color here, and all the pixels corresponding to the vehicle have a different color here. It just shows that it's being segmented into a different class. Segmentation can, in a lot of times, like mostly it can help us find the free space, the drivable space here, but other than that, it can also help us refine our object detection. because here we are getting the object's exact dimensions. Um, so this is the right corner image. This one is for depth estimation. It's just giving us a heat map based on where the vehicles are in the image. So how far are they away from us, or how far are the other objects that we are trying to detect from the eco vehicle. So this is what depth estimation is about. Sometimes or mostly uses a whole lot of these sensors, lidars and radars, but in the simplest sense, from a computer vision standpoint, we usually just use two cameras, like a stereo camera setup, where the cameras are placed in a straight line. It's very similar to the human eye system. So that's mostly how, or that's the basis behind how human eyes detect the distances or the depth in the object in the scene. So two cameras placed a few centimeters or a few, yeah, a few feet apart maybe. They look at the exact same scene, but with slightly different viewpoints now. So comparing these two, we try and find the distance to the object. So that's depth estimation from a computer vision standpoint. This can also be done using just a monocular camera with a single camera, using all the trigonometric functions, but it's usually more accurate when we use like two different cameras there. And yeah, object tracking is also something we'll look at based on how time works out for us. But object tracking is just keeping track of the detected object. So once you detect it, it's going to like stay in all the frames here. So you're going to like keep tracking it. And the key thing here is object tracking is mostly the only application in this whole area that requires temporal information, time-based information, or a sequence of images in our case. So looking into the computer vision aspect, before we dive in deep into vehicle detection, what is actually an image to a computer? For a human, we can definitely look at this and say, okay, this looks like a face. It's probably just a very pixelated version of a face. But for the computer, it's just going to be numbers. Every pixel here is assigned a value between 0 and 255. And in the end, all it sees is not this image, but just a bunch of numbers. So it could look like it's pretty difficult to like read and manipulate these numbers, but this is what a computer understands. So this is what we'll be manipulating going further to actually get everything that we want out of the computer. So vehicle detection, this is like one of the key topics today to talk. We'll be looking at different methods to do vehicle detection. Okay, so it's going to be like the first two methods here are just based on pure computer vision, very traditional methods, and probably not in use anymore, but the building blocks of anything that's based on neural networks. And we'll be looking at two different neural network-based detectors as well. So the first one was cascade object detector using hogged features. So what's a cascade object detector? Let's probably like start with what we feed into a cascade object detector. So it's going to have like positive and negative images. And when I say positive and negative images, this is going to be a vehicle detection algorithm. So everything that we feed in here would be images of vehicles, and a set of all these would make positive images. Negative images is usually defined theoretically or from a very academic perspective as just images that's devoid of the vehicle, the object that we want to try and detect. But from a training perspective, it's always easier to give it instead of like just giving it a negative image of say a cat or a dog as for vehicle detection. It makes more sense to like give it images of like empty roads or empty parking lots, because that's where we would ideally find a car. So this is easier for the system to like train itself. So, and this being a very simple computer vision based algorithm, it's pretty important that we train or we tune what we given to the system here. So data is definitely a big deal, and this would be like the positive and negative set that we give into the cascade object detector. So what the cascade object detector is it's a concatenation of many weak classifiers that are placed sequentially. And these classifiers can be made of like many features. We'll be looking at two of these in detail. Histogram of oriented gradient, hard like features, or like just local binary patterns of plus and 1 and 0. And the metrics that we use here are like true positive rates, false alarm rate, and the size of the object that we are trying to detect. And so this cascade object detector is going to have like a series of weaker classifiers, every classifier trying to like detect something out of the images that we given to the vehicle, so to the computer. So it tries to do that, and the way it localizes is once it learns if it has an image or if it has the object of choice or not, it runs a sliding window detector across the image. This is also a pretty old method to do it, but what it does is just runs like a small box or a filter across the image completely. It's not a filter actually, it's just a detection box. So it runs that across the image for every pixel there to look and see if it has the object that we're trying to detect. So this is Cascade Object Detector. And the first feature is histogram of oriented gradients. And here, like we can see in these images here, what it's trying to capture, just as its name says, it's the orientation of the object. So we can see here, it almost looks like the orientation of a vehicle from the rear portion. Point to note, though, it is very sensitive to aspect ratio because it's learning the orientation here, so we can't like make it detect, or we can't expect it to detect objects of different aspect ratios or even different orientation for that matter. Since it's trying to capture the orientation here, we can't train this network with a lot of rear images of a car and then try and ask it to detect like the side pose of a car or something. We'll look into like the next slide has results, and running this on like images that were locally collected from a normal car mounted dash cam that we had for the competition. It looks, this has, so we look into the metrics soon, but just looking into the images here, I'm not sure if the boxes are very clear uh, in the slides here, but what I can see is there are like some vehicles that are very clearly detected, or most of the bounding boxes are vehicles that it detects, except in this image where it randomly places boxes everywhere over the image. But there are also cases where it uses like, or where it has like two boxes for the same image. And definitely, yeah, there are vehicles here, like we discussed just now, there are vehicles that are not completely that we don't see just the rear portion of. We see like some of the sides of the vehicle and the rear portion, and those vehicles are just completely ignored. It doesn't really detect vehicles like those. And the metrics for object detection here we use is precision and recall. Precision is, in simple words, it's the number of it's a number of correct results that the algorithm throws divided by the number of all the results that it throws. In simpler sense, I would say having a really good precision here says that everything that's detected is almost always a vehicle. It's not like a random box that it draws. It's mostly in 85% of these cases, it's going to be, it's a vehicle that it detects. Poor recall though says that it leaves out a lot of object, that its true positive rate is very low, and but it doesn't really throw a lot of false positives, which is good for us. And so it has a good precision but very poor recall. The next method is hard-based, hard-like features. This is a very simple method compared to even hard. It's basically just placing. It's trying to make use of the pixel differences in pixel intensities across the image, and it targets like various parts of the image to try and find if that's a vehicle. Like say tires would have a different pixel intensity as compared to the body of the vehicle. This hard lake feature, though, it's used. It's very fast in its operation. The the speed of detection is very high here, but in most cases, it's used for local pattern identification, like say face detection, because that's going to be a very small area that's trying to detect, and the intensities are much more visibly changing there. So hard lake features are traditionally used only for local pattern detection that way. But I just tried using it for vehicle detection just to see if we would get anything at all, because the one other requirement for all these ADAS systems is they have to be real time. We can't detect a vehicle or something 4 seconds after it goes past us. It has to be right in that instant. So since hard is usually very fast, I went ahead and tried using hard like features there, and it had both word precision and recall. Like you can see here, it draws like huge bounding boxes over images or cars, and sometimes it's not even cars, it's just randomly drawing bounding boxes here. And if it's not tightly bound, most of these boxes are also rejected as the correct detection. So which is why we don't have like a good precision or recall here. But then the speed of detection is very high. The next two methods, in fact, are going to be neural network based methods, and they will hopefully will not see like very bad results like we just saw, because neural networks are relatively very new field, or at least it became popular for ADAS very recently with the growing popularity of all the compute that we have, all the GPUs. So neural networks usually in its very basic sense is just layers, or it would have like input layers, a lot of hidden layers in between, and output layers. It takes in the image and runs it. So here it's convolutional neural network. So convolution is just going to be a feature or a filter. So it runs convolutions over the image. The GIF here shows how convolution works. It's just assigning random weights to each of these pixels here. This would be the first pass. It would do that and generate like a convol feature. And it uses this convol feature all the way to the end. And in most of these systems, it's called supervised learning, where we know what we're expecting out here. When this image is a cat, we know that we're expecting a cat here. So with random weights initialized, it goes all the way to the end the first time. It checks if it's a cat. And definitely with random weights, it's not very probable that it actually detected a cat there. But once it sees once it sees the output, it knows the error, and that error is propagated, or it's called back propagation algorithm. It's propagated all the way back to the input, and convolution happens again. And this time, the weights are assigned with a little more smartness than it did the first time. And this process is repeated like multiple number of times with a huge image data set, a large number of images there. And it thus learns to classify the image or like detect the object properly. Other than convolutions here, we have like a few other layers. It has something called the activation layer, or activations. It's called the most, or at least one of the more popular ones is the ReLU. It's what makes a neural network. It introduces nonlinearity by saying anything below zero is just going to be ignored, and then it increases linearly after that. So that's ReLU. And we also have something called pooling layers. It could be like max pooling or average pooling, where this is mostly to like reduce the size of these features because it can quickly explode. So what they do is they take like blocks of these and either take the max value out of it for max pooling, or take the average value of all the 4 blocks to keep the feature size at a minimum. So this is convolutional neural networks at a very quick glance. The object detectors that we're going to see today, the first one is a glib network. It's an open source computer vision library for neural network for object detection, specifically for vehicle detection. And it uses something called the max margin object detection loss, which is a little novel to this object detector. But the whole pipeline that they have there is also very novel, at least at that time. uh, they have they came up with this cool idea of using a tiled image pyramid. We look into what that is very soon. But yeah, in it just uses an image pyramid, downsamples all the images, applies convolutions, and then applies the loss function finally. And it's a pretty dense network as well. We saw like one convolution there, but this has like multiple convolutional layers, and it keeps downsampling over and over. This would all mostly be the pooling layers, bringing down the sizes here, and it goes all the way to like one feature map. So from an RGB 3 channel input image, it goes all the way to like one final feature map here. What it looks to the user though is the first image here would be the input. This is what we'd want to detect the objects in. And this creates something called the image pyramid, which is it downsamples the image, it brings down the size of the image. Uh, Depends on the input image size. I think here there are like 16 different downsamplings that's happening or something. But it basically downsamples the image, creates this new image, which is called the image pyramid. The reason for doing that is uh, the scaling. So an object that looks so big in this image could look very tiny in like smaller images. And if it can learn and detect objects in both these images, then it's a win for the system. It's going to be able to detect objects of varying sizes. So that's one of the prime reasons they do this image pyramid formation. So this is the first one. An RGB image is taken in as input, it's downscaled to create a Gaussian pyramid of images. These images are placed in a tile, and that's inputted to the neural network, which will then detect, it will use the MOD loss there and detect the objects in each of these images. And it throws a heat map where it thinks there's an object. The third image here is just an overlay of whatever it throws as an output on the original input image that we had here. And finally, we just use a non-maximum suppression to like make sure we don't detect the same object multiple times, and then draw bounding boxes to say, okay, this is where the image is at. So here it at least detects like these two vehicles very clearly, and that is where it draws the boxes over. The results, they look, it has really a good precision. So whatever it detects as a vehicle definitely ends up being a vehicle. It doesn't do any false detections, and it does a good job with the orientation as well. It detects something in the side which doesn't even look like a vehicle to me. And also in like very dark images where it's a little difficult for the human user to like detect vehicles, and it does that. So everything that it throws as an output is definitely ends up being the right object. So it has a very high precision. The recall is a little low though, because there are vehicles here that it that it really doesn't detect, and also like partially just like one wheel of the vehicle here that it doesn't detect. But the major disadvantage of this method though is it's not for real time. It's very slow. It runs like 7 seconds for a single frame on the CPU. It'll definitely speed up on the GPUs, but it's still not for real time detection. So the final vehicle detection approach that we have here is YOLO, and it stands for you only look once. We'll look into that just to motivate why we need YOLO. The initial or early object detection methods, like once right after Hog, people wanted with the rise of deep learning, there were like many ideas to like replace Hog somehow. The first feature that we saw there, they wanted to replace all those Hog-based classifiers with a more accurate convolutional neural network-based classifier. So it started with that. As one problem though, CNNs were like very slow at that point. Sometimes they still are, and computationally very expensive. So it's almost impossible to like run CNNs on so many patches of this image here. So that was a huge problem. So as a solution, what they did was, in the first one, it's called region-based CNN. They extracted region proposals first from an input image, And for this, they use something called the selective search algorithm. And for every input image there, I think they had like 2,000 patches that they thought could be like relevant places to look for objects. And these patches were then fed to the neural network. And this is, instead of like running it on multiple patches across the image, it was only running on like 2,000. Oh yeah, it's only 2,000 patches there that it runs on. And the CNN then outputs, if it's going to, it classifies the objects there, and also like localizes and tells us where exactly it is. So this was like the first version of it, and this was pretty slow running. Uh, it it took like the selective search algorithm here took like a very long time to run real time. It couldn't easily clear as a real time algorithm. So they came up with like more optimizations there. The main part where it loses time is in the selective search algorithm when it's trying to like find the best patches to detect. So instead of that, they came up with something called a region proposal network. Um, this region proposal network is a very small convolutional network, and it's trained to like generate regions of interests. So it does that. So it's still like a two-step process. Now you have an input image, you generate all these region proposals, and then use the CNN on that to find the object. So this is like a two-step process. And the method that we're going to talk about next, YOLO, it stands for you only look once. And the rationale behind this name is it's a single step detector. So we saw like two stages there, like region proposal and then doing the CNN. YOLO doesn't do that. It takes in an image, directly outputs bounding boxes here. And to do this, it's a 32-layer deep neural network here. And it also, since it's a single step detector and with a whole lot of optimization, it runs at real time, it runs at 45 frames per second on a GPU. And they also came up with a lighter version of it called the Tiny YOLO with just 9 layers in here. What it does, what YOLO does is it's a single neural network. It predicts the bounding boxes and the class probabilities for all these bounding boxes that it outputs. And each input image here, it is divided into n cross n or s cross s grids, like too many grids here. And each of these grid is known as an anchor. And for each anchor, they have like k bounding boxes. And these anchors are responsible for actually detecting the objects there. This is the architecture of YOLO. It's a 32-layer neural network, and I think it has like 24 convolutional layers here. And it was initially evaluated on the Pascal VOC dataset. And it has like a lot of convolutions to extract features initially. And the last layers then output the fully connected layers that we have here with every node from the output connected to every node in the input and the output nodes are all fully connected. They output the class probabilities and the coordinates that we're looking for. So this is YOLO, and YOLO comes out with pretty good results and real-time results on where the objects are. What I found funny though here is for one of these images, it was trained on multiple classes, and it even detected the driver inside the vehicle and said, yeah, that's a person. At this point, I think we have some more time. Would you want me to like stop and take questions? I have like a few more slides here, but not sure if I'll have time for questions if I go over all that. All right, if there are no questions at this point, I'll just go ahead and cover the next set of slides as well, and we can talk later. So object tracking is the next part of object detection. The first method that we tried here was a very simple optical flow method, also a computer vision based, a very old method in computer vision. What optical flow does is it's looking for all the movements between like two images. Like it takes two images and it sees the movement of these pixels or brightness patterns there. So in a sequence of images, it does that, and that's optical flow. And in this image, what we do is we take in an input image, we threshold it first to just find blobs of vehicles. That way, we don't have to like track every single pixel in this image. And all these blobs are the ones we go ahead and track to see how it's moving. So very simple method, very naive way of tracking. But this was the first one we tried here for the EcoCar competition, and it worked decently fine, but there are a lot of issues associated with using, like optical flow. For instance, object occlusion, like if this car is occluded by a different vehicle or something, then we completely lose track of it. It's going to become like one full blob there, and we'll no longer be tracking this object. Or say, we also assume that the camera is very steady, the objects are very steady there, not everything is moving around. And in a real-time vehicle setup, that's difficult because the eco vehicle is going to move, and also the vehicles on the scene are going to move. So it needs like a lot of robustness in making sure a method just as simple as optical flow based on computer vision or the camera inputs would work. So that was a problem. And large movements, like sudden obstacles, like say there's a deer on the road, that would be a problem. Or just illumination changes. You go in and out of a tunnel, there's going to be a whole lot of illumination changes, and doing the thresholding here would become a problem. Like just detecting the blobs would be a problem. So these are like some of the very basic issues we had with optical flow, but nevertheless, for a quick start to just do a proof of concept, it works fine. There's something else called disparity. We were speaking about stereo camera setup with two different cameras kept apart but looking at the same scene. So the next method that we use for object tracking is a neural network based method as well, and it uses both optical flow as its background and also disparity. So disparity is, so there are going to be like two images, the left and the right camera images, and they're both looking at the same scene. What it does is it calculates the differences between these two images, the left and the right, and it throws these images called disparity images. So these are the building blocks for the object tracking method that we have coming up. This is something called the scene flow algorithm. So since we already have the YOLO part here, what we tried doing was used a neural network for object tracking and used inputs from YOLO to like actually refine whatever we're getting out of it. So what SceneFlow essentially does is uses time sequenced images. So we have like T-1 and T images from both left and the right camera. So from a stereoscopic camera setup, we're getting time sequenced images, and both disparity and optical flow are calculated on these images. So DispNet is a separate neural network that tries and calculates disparity, and FlowNet does the optical flow calculation. And with these two networks, just calculating optical flow and disparity improved a lot because it's now a neural network that's trained to like do this task instead of just naively doing it with a single or two images in a series. So using a series of images here, the CNNs are then trained to learn scene flow. Scene flow is like a combination of both FlowNet and DispNet put together, and this is used to track the object. So what scene flow looks like is this. Essentially, it's like two different images, the left and the right, and from a stereoscopic camera setup, it's passed in, and these are used as inputs for DispNet. And for FlowNet, just the image sequence that we feed in initially becomes the input. So it uses that, and scene flow, we know like, so optical flow is calculating the 2D motion field of points in an image. And scene flow is exactly doing the same thing, but just in a 3D way, now that we have both disparity and optical flow built into it. So it's doing it in a 3D fashion and improves the accuracy there. And a cascaded version of these two, the FlowNet and the DispNet, is what is called the scene flow. And going back to the previous slide, so with scene flow, we're also adding YOLO now. So YOLO is detecting objects. And the beauty here is there are like multiple neural networks here. DispNet is trained separately, FlowNet is trained separately with its own set of inputs, and YOLO is trained separately to like detect vehicles. And then putting all these things together from a pure software perspective, YOLO detects objects and SceneFlow tracks them, and it uses images from YOLO, so it's going to be refined at this point, and that's how we track objects. What it outputs, though, is something like this. So it outputs all the depth and the 3D motion vectors for all the visible points in an image, and it's like a heat map now, so we can like see where the vehicle is moving, and then just draw a bounding box over it to track the object. So yeah, that's mostly what I had for today. Yeah, any questions are welcome, and any comments from your side definitely welcome.
There's one question in the chat box.
Oh, let me.
Should I read it for you?
Yeah, sure.
Okay. How can we control skidding on oily or slippery surface? Because even if we can use ABS system, it can't be controlled.
That's actually a really good question. And yeah, not just oily surfaces, especially like snow-based surfaces. That's still something we're trying to solve. It's a active area of research. And there's also a lot of accidents that happen on the road today just because of not being able to control the vehicle in a snow-based setup. But this is something to do with the wheel traction itself. But currently, like the research areas that are looking into this is trying to find the terrain. Like the first part here would be to like actually find the road surface to see if it's a hilly area, if it's grass, where, or if it's just road or a slippery surface. So that's the one we're trying to like detect first, and once we have a good control over that, I think we can take corrective measures to make sure we can still control skidding in like slippery surfaces.
Yeah. Okay. There's one more. How necessary and important is it to have manual overpower mode?
Is manual overpower mode something like a driver takeover? I'm not sure I get the full context of the question.
Neeraj Yadav, if you're there online, you can please ask it. You can clarify the question. Meanwhile, there's another question. Ma'am, while object tracking, how are we doing time-based analysis?
So in object tracking, we are giving it like two different images. Like, so images are captured at every time instant, and the input that we are giving to the neural network would be from time step t and time step t-1. So like it compares these two images and finds the movement in these two images. So that's the optical flow part. So we are inputting like a sets of like two images from each of these cameras there. So it takes in temporal information from images and then calculates the object position based on that.
Okay. Another one. How this system will be effective in highly congested areas, hilly areas, and WBM roads?
Okay, not sure what WBM means, but
Yeah.
okay, no issues. So in highly congested areas, we are currently looking at, this is more of an L3 application at this point, but the idea there is to like let the system completely take over in congested areas, because there's not going to be a whole lot of movement. The vehicles are going to move very slightly there. So the idea is to let the computer or let the vehicle completely take over and detect. So it has all these sensors, so it knows relative to vehicles in front of it where exactly it is. So it's going to like move very slowly in slow speed. It would be a slow speed application, so it would move there to like find where the vehicle is currently, localize it, and then navigate across the traffic very slowly.
Okay. Which market segment is more adaptive for driverless vehicles by 2020? We are already in 2020, so probably.
Which market segment, as in, the continent? Is it?
Maybe the
Okay.
continent, yeah.
Good question. I think it's coming more from a personal point of view and not from anything to do with my company. But I'm thinking, yeah, definitely United States is leading this. There's a whole lot of research happening in the Europe as well, but and Europe is focusing more on the infrastructure itself. It's trying to like make sure a connected vehicle setup works fine. But I think from just the AI perspective, US is definitely ahead of all the other continents there.
Okay. There's one more. How do driving simulators remain relevant in an age of automated vehicles?
So currently we are using, so driving simulators are a huge benefit actually, because they are generating scenes for us. So in a driving simulator, you see like real world scenes right outside you. And these are usually generated just using a gaming engine. And for at least a deep neural networks perspective, the simulated images are like highly necessary for us to like train and test our systems. And also, so say there are like conditions which we definitely can't go on the road and collect. Like, so this is like a summer right now, and what if I want like snow data to like run one of my neural networks on it? So in that case, all these driving simulators help a lot, because we then get to generate those data. Uh, it looks very real. There's also something called GANs out there. It's generative adversarial networks that make these simulated images look very realistic. And using that, we then go ahead and train our neural networks accordingly. So simulators are like a huge benefit. I think they are even like a good add-on point for everything that comes from automated vehicles. But that's it again. Just driving simulators to train a person to drive is probably not going to be relevant going forward, but it'll probably give people a good. There are definitely other applications I can think of. Like people get a lot of motion sickness in these vehicles. We are also used to like holding the steering and driving. We are used to like controlling the vehicle ourselves. So when this is not the case anymore, and when you turn the seat around, people are then going to like, there are definitely like some people who have a lot of motion sickness just sitting in the back seat, and when you turn seats around, it's going to make a huge impact. So from driving simulators, if you're not going to teach people to drive, we can always like collect data as to how people react, or if they're going to be distracted, where their eyes are looking at, if they're paying attention to the road. So there's like a whole lot of applications that can come just out of driving simulators. Oh, okay. Let's say there's one more question here. Automation in aviation versus in vehicles, what are the differences and similarities from human factors perspective? How is it possible? Okay, so that's the first question. Okay. Aviation is definitely, they're leading this thing, I would say, because most of their systems are already automated. So it's definitely the front runner there, aviation. But from a vehicle standpoint, it's a little more different, because we have like a whole different setup here, and it's the traffic, the way people behave, and in a lot of scenarios, like just having, I should probably not say this, but then there are like animals on the road, stray animals, sometimes like pets on the road, things like that, and those are something we have to be very careful about when it's driving. So the similarities, though, is both these industries are trying to automate things, but while making sure the safety of the customer is like the first important priority there. So that's definitely a big similarity, and the technology that's used is also mostly there's a lot of similarities there. But that's it. The whole situation or the scenario that we're looking to is completely different in these two situations. Okay, I think I'm losing track of the questions here. How this technology can be a future technology to India, particularly for budding engineering students? Oh, definitely. So, so currently, like from a job opportunity perspective, there's a whole lot going on in just the ADAS space. Fully autonomous driving maybe still from a job perspective a little away, but there are also like a whole lot of research that's going on there. So for anybody who's focusing on research, I think a completely automated system research, they should like focus more on like the sensors used, processing these sensors, and a whole lot on machine learning, because automated systems are going to be solely fueled by machine learning there. So that's something they can totally focus on. But for students who are more into like embedded, in my own background, I'm more towards embedded and more towards like putting things into production than doing a whole lot. I do a little bit of research, but then it's more, my research is also focused towards putting things to production. So in that case, I would say learning how these neural networks work on GPUs, and for like topics, like say project topics or something, if you're looking for optimizing these neural networks, pruning these neural networks. So neural networks are huge, and not all of them can fit on the device, and let alone one neural network. They're going to be like many multiple neural networks running on the same system at the same time, because we'll need to like detect vehicles at the same time, find free space, do a whole lot of things. So there are going to be multiple neural networks running in parallel. So it's always important to make sure these networks don't take up a lot of space, don't take a whole lot of time to run. And current research topics in that area are mostly quantizing neural networks, bringing them all the way to like floor 32 down to int8, and also that's one part. And then pruning the networks itself, making sure we remove all the unnecessary layers once it's trained properly, just keeping the fixed weights there. So that's also an active area of research right now. And just looking at it, I would say like every stream of engineering can have like one application in ADAS systems, like communications, for example, in the whole connected space, that's processing everything on the cloud, bringing it back from the cloud, the whole interface that goes on between the vehicles and the cloud, that's also going to be a big area of research going forward. Not sure what an automation hamper manual job is. Can you elaborate on that? Okay, I see. Yeah, that's a common area of debate as well. Like if AI is going to take over manual jobs, if that's going to happen. But in my personal opinion, no, it's not going to happen. People are probably going to have like more specialized jobs to work on. Definitely, it is commonly misconceived that automation kills job opportunities, but maybe not the case always. I would say like we did not really have mobile phones up until a point. We were all like, we had a notepad, we wrote down all the numbers, and it came up in stages as well. Like we initially had those digital, forgetting the name of those, the digital pads or something, and then it went on from that stage by stage all the way to like a mobile phone now. And this is, every time there's a new technology that comes to disrupt the entropy in the market, it's always feared of, it's always thought about as that. It's a common question if AI is going to like kill manual jobs, if robots are going to take over humans. Maybe not. I would say it's still humans who are doing all these, humans who are still controlling all these things. So I'm sure with a whole lot of inputs from you, the students back in India can also like work on different areas here, make sure we advance automation and we stand at the forefront of this, and actually take like a good lead in how automation shapes the future rather than letting automation take over manual jobs. So looking to a question ahead about the sensitivity of actuators. Oh yeah, that's totally true. What you have there, not just sensitivity of actuators, even sensitivity of cameras for that matter, or any sensor that we put in the vehicle, they all have to be like perfectly tuned and true for an electric scooter. There is a whole lot of lag that's happening right now, but imagine if the same lag happens in a vehicle setup, and if we detect an object 5 seconds later, or if we just fail to take an action. We do see all these news coming about these days, like how like during testing something went wrong, but people are still taking like utmost precaution there. They have like a safety driver initially to like make sure all these things are going fine, but sensitivity is a real problem, and they all have to be tuned perfectly, and using like really good ECUs there, which can process all these. So in an automated driving setup, there's going to be like multiple uh, sensors there. They're all going to be like blasting information back to the system. So the central computer that we have, the ECU, should be capable of getting all these things from the system and still managing to process everything properly, giving it back in real time and not malfunctioning. So definitely involves a lot of research and a whole lot of technological improvements in from the GPU's aspect as well, just to make sure we do everything in real time and don't mess things up. Yeah, looks like that's mostly all the questions. Okay, there's one more. As vehicles will be communicating with other vehicles and various other sources can, oh yeah, hacking privacy concerns are a big problem as well. There's, yeah, the hacking part is why connected vehicles hasn't progressed so far, as at least as quick as autonomous vehicles have, because it's not just about internet hacking there, but it's also about like the information that I share with, like, as an OEM, say Ford Motor Company has its cars on the road, and there's GM's cars also on the road there. We think we're only like sending from in a B2E sense, or from in a B2X sense. We feel we're only like sending out like some parts of technology, but or some parts of the results that we get. But definitely, it's a huge problem there, and people are still fighting over it for all the privacy concerns to make sure nothing is stolen. And they're also like trying to come about with writing a standard there to make sure what can be shared, what can't be shared, because this technology is still very naive. So it needs a lot going forward, and people are like figuring that out right now. And yeah, a lot of security, cyber security folks are also working on this to make sure anything that we send out is very reliable, because now it's not just sending out to another vehicle, but it's sending to the cloud there, and you never know which link can get hacked. Anything can. So there's a whole lot of issues there that people are sorting out as well. But then the whole aim here is to just make sure user safety, users' data privacy concerns are all taken care of. So, which is also a reason why this field is not advancing as fast as it can. But there are also like definitely companies like Tesla that are just going all in there and putting things out there, testing it out on the road real time. Sometimes it's failed, sometimes it doesn't. But in the end, I think it's just a big learning process.
Any more questions from the audience side? Participants, any more questions? If there are no questions,